Hello and welcome to the TID Water and Power Podcast. I'm your host, Constance Anderson, and on this month's episode, we're discussing substations. You may have seen TID substations in your neighborhood or while driving in our area, but you may not realize the important role they play within our system. Strategically placed throughout our electric service area, substations are critical for the transmission and distribution of reliable power to more than 240,000 people in our community. On this episode, I'm joined by TID Senior Electrical Engineer Janis Scott to discuss how substations work, the role they serve in TID's electrical system, and how we're upgrading substation infrastructure to maintain reliability for our customers. Janis, thank you for joining us.
Thanks for having me.
All right, excellent. So why don't you start off, if you would, by telling us a little bit about your background here at TID and where you were before you got to TID.
So I've been with TID since October 2010, so coming on 15 years.
Wow, congrats.
Thank you. I was hired in the training coordinator role in power operations as an assistant electrical engineer. There I was responsible for learning about the NERC regulations and how they apply to our power control center operators and the types of training that they required and hours that they needed to be tracked in order to meet the minimum requirements for their role. In 2013, I was actually lucky enough to be in the right place at the right time, and having been invited to come to the substation engineer role. So it just so happened, I think that usually with the substation role, kind of everybody wants to do that. And it just happened that even though I was pretty early in my career, that people passed.
Excellent.
And I was lucky enough to land on the role, and I've been here ever since.
Excellent. And how about before you came to TID?
So TID was my first opportunity as a utility engineer. Prior to that, I was living in Tennessee. My husband was stationed in the Memphis area, and I was working in manufacturing there. And prior to that, that was my first job out of college. I got my electrical engineering degree, graduated in 2008 with a power emphasis. I came into power simply because I was 6 years in the nuclear Navy in the nuclear field electronics technician. And so my role there was a nuclear reactor operator.
Wow. And
so from that, I just, I really appreciated how power was developed, how power was distributed, all of the things associated with power. So I definitely found my love for power in the Navy, and I'm very happy to be working in power now.
Right on. What a cool backstory. That's really interesting. And thank you for your service, by the way.
Oh, yes. Happy to do it.
All right. So before we get into all things substation, I think it'd be good to give our listeners a quick overview of the district's electric system. So can you kind of give us sort of the makeup of what that electric system looks like?
Sure. So TID has a pretty large electric service area, considering a lot of the smaller municipalities in the system. We have 662 square miles that we cover. That goes from the Tuolumne River to the north and the Merced River to the south. We also have portions of LaGrange and feeding up to Don Pedro on the east. And on the west, we have Patterson as our service area.
Wow. So that does cover a pretty good territory then. And how about when we're talking about power, we're going to talk a lot about transmission lines and distribution lines. Can you give us any quantifiable numbers on how long those lines are?
I don't have the breakdown exactly for the transmission, but we do have three different voltage levels of transmission: 230 kV, 115 kV, and 69 kV. And that makes up 379 miles of transmission. And then within that 662 square miles, we also have 2,300 linear miles of distribution.
Wow, that's a lot. And I'm going to ask, and we're going to double back to the voltages you just mentioned here in a second. But how many substations and or switchyards do we have in our service territory?
We have 29 substations and switchyards within our service territory. And that's going to include switchyards that are fed by generating stations, as well as the Oakdale switchyard, which is a tie point between our external neighbor, which is City and County of San Francisco in that vicinity, and then the rest of them are all substations.
Okay, excellent. All right, so doubling back to that voltage note that you made, can you give us kind of a third grade level description of why we work in different voltages and what those represent?
Yeah, so the main premise to consider is that power is power regardless of the voltage level that it's at. So whether you're at a higher voltage level or a lower voltage level, the power that's required is going to be the same power. However, there's a calculation that goes into power, and part of that is current and voltage. So when you're at a higher voltage level, you're actually at a lower current level. It's a mathematical equation. And so with that, when you're able to transmit at higher voltage levels, your current level is lower for the same amount of power. So at lower currents, you are still, you're able to do a few things. So when you're able to be at lower current, then you can transmit along a smaller line.
Physically a smaller line.
Physically smaller line. So there is less cost associated with those smaller lines to transfer that much power. You are going to balance that with how much resistance is in that wire, because the higher resistance you have in that wire, meaning the physical size of it as it gets smaller or bigger, you either have more or less losses associated with the current that's coming through there. So if you're able to transmit at a higher voltage level, you are doing so at either a lower cost or amount of lower losses. And so it becomes easier to support that power transferring from one voltage or from one place to another.
Okay, got it. Thank you for that. All right. So what does a substation actually do, and what is its role within our larger electrical system?
So substations play a very critical role in the electric system because that's where the transformation of power actually occurs. So where we go from one voltage class to a second voltage class. And generally there are different types of substations. In TID, we have transmission substations, which means we're going from one transmission level to another transmission level, either lower or higher. And then we also have distribution substations, which go from a transmission level down to our distribution, which is 12,000 volts is what we consider our distribution voltage. So a key part of the substation, as I mentioned, is that's where that transformation happens. So we have transformers that are located in the substation that will step the voltage from whatever voltage we're at, either down or up, depending if we're coming from the transmission side or coming from a generator and we want to put power onto our system.
Okay, excellent. And now you mentioned that in some of the substations where they're distribution substations and they're actually taking that higher voltage and dropping that down to then be transmitted to the community.
Right.
Why do we need to do that to get it out to individual houses or businesses?
So at the higher voltages, while that does help from a current carrying capacity that we kind of mentioned, you're also much bigger in size. So as you get higher and higher in voltage, there's more of a chance that power, that voltage can leave the bus or the switch or the element that it's at and actually jump to a neighboring element. So it's higher off the ground, further apart. We have bigger and bigger equipment, more and more cost associated with that equipment there located within the substation. So when you're going from a distribution or going to distribute to our community, we don't physically have the space to do that at that voltage level. And then these transformers that we have, I mean, the larger the step that it takes to go from, the bigger those transformers have. So again, we don't have space in our community, nor does it make sense from an economic standpoint to distribute that way. So we actually distribute at a lower voltage. And that lower voltage means that we're smaller spacing, smaller equipment. and able to mostly be handled on our poles or underground facilities that we have out there, and space within the community to do that.
Okay. Interesting. All right. So now, in addition to either transforming the power up or down to a higher or lower level and distribution, what are some of the other functions of our substations?
Definitely protecting our electric system. All of the protection all of the protection on the TID system happens within a substation. So that occurs by creating points or using instrumentation to monitor what's happening on the system, and then causing trips to isolate the sections of the system that are faulted or have been sensed to be faulted. So that happens with very large circuit breakers that are located at either end of a transmission line, and those are physically located in the substations.
All right, thanks for that. So now let's talk about the different components of a substation. You just mentioned circuit breakers. What else might we see if we were wandering around a substation, which I don't recommend any of our listeners wander around a substation. It's a very important and dangerous area if you don't know what you're doing and what you're dealing with. But if we were to look from a safe distance, what sort of components would we see?
So what you're going to physically see is the transformer, as I mentioned, circuit breakers, as I mentioned. I did also talk briefly about maintaining that space and that distance that we need in order to bring the lines in and have a safe, continuous operation of those lines. Those lines are going to be spaced apart. They're going to land on a structure that's going to be pretty far above the ground, and that's for personnel safety, but also to ensure we don't have a situation where contact's made with the ground and we have a faulted condition there. There's going to be the circuit breakers, which cause our protection, that cause our interrupting capability. And then we also have disconnect switches, which will isolate equipment to allow us to work on it and maintain other portions of the systems up. Within the station, you're going to see, as I mentioned, structure. You're going to see bus, and bus is the way the current travels, the power travels through the system, either on wires or on what looks like a pipe bus.
Okay.
And those are supported by insulators. So you'll see either porcelain or polymer insulators. You generally see those standing on the structure, and they hold up the bus, and that's so that you have that gap to make sure that you're not going to see that fault go to ground. They also support the bus so that it is able to survive faults and anything that the system might see. We're going to have, for sure, voltage transformers out there. We have instrument transformers, and usually that's in the form of a voltage transformer as well as current transformers. The voltage transformers will attach to the bus and sense what is actually is the voltage that is sensed there, and that's transformed down to be used by our protective relays. We also have current transformers, which are usually part of the circuit breaker, actually, and that's sensing the current that's either coming in or leaving on that breaker, and again, is brought into our protection system.
Okay.
And so with that information, not only does it provide cues for our protection system to respond to, but it's also providing system information for our power control center to monitor.
Okay. Now, speaking of kind of the monitoring and knowing, the system being able to report kind of what's coming in and going out, how does that all work? Is there somebody who's monitoring that power that's coming in and going out? How do we know when there is a fault somewhere in the substation?
So I think that's kind of a two-part question. We do have someone who's physically monitoring for alarm conditions where, let's say, if your bus is supposed to be operating at this voltage, but you see that it is dropping down or exceeding that voltage, there's alarm set points that are programmed in that will alarm in the power control center. Same thing with current. If a current limit is exceeded, power control center becomes aware of that. That doesn't necessarily mean that there's a fault on the line. It might have something to do with the configuration of the transmission at that time, or if you see something that's heavily loaded and it's just dragging the voltage down in the system somewhere. For a fault, that happens at a much, much faster pace, faster than any human can respond to. So that's like sub-seconds, somewhere in like the milliseconds kind of standpoint. Wow. With that, the protective relays, depending on the type of relays they are, they're looking for those cues that I mentioned. We do some protection across communications, and that is basically a relay on one side of the line and a relay on the other side of the line talking to each other. Okay. And they're making sure they're seeing the same thing. And if they're not seeing the same thing, then they cause an interruption to happen for protection purposes. The other thing that you'll be looking at is like the current and the voltage that I mentioned that are coming in. And that's something called impedance. So when you see the voltage drop down really quickly and the current spike up, there's a good chance maybe a line fell to the ground or something leaned into the line, and now there's a direct path on that line into the ground.
I see.
So you use that voltage and current together to determine that the protection needs to happen, and then it causes that interruption. And you want those things to happen as soon as possible. The faster the protection, the less likely that you're going to see additional cascading outages as a response to that.
That makes sense. Okay. All right. So how about the difference between a substation and a switchyard?
Sure. So switchyards are where switching happens in the system, whether to reconfigure a section of line or whatnot, but they don't tend to have substation or transformers within them. So usually when you define a substation, it includes a transformation going from one voltage to another voltage class. The switchyard, you're going to see multiple lines coming in. You're going to see different switches that would change the configuration, maybe connecting one line to the system or one line to that system, whichever that switchyard is designed for. The other thing that you'll see sometimes, as is the case with our Oakdale switchyard, we have our metering point where we intertie with our neighboring balancing authority. Mentioned the city and county of San Francisco is our balancing authority there at our Oakdale tie. And so we have a really high accuracy equipment that is looking at that current flow and the voltages there. And those are very regularly calibrated and agreed upon so that we are confident in the revenue process between the balancing authorities.
Okay, great. Interesting. Okay, so you mentioned that TID has 29 substations in our service area, and I'd like to talk a little bit more about those. First of all, how is it determined where a substation will be located?
So that's going to vary depending on the need of the substation. If you are tying to a generating facility, you want that switchyard or substation to be tied in right into that generating facility. You do not want to carry more power than you need on those at that lower voltage. You essentially want to step right up to the system for losses and honestly, just because it's easy to locate a switchyard there at the facility. If you're talking about a distribution substation, that's a little bit more nuanced. There's a lot more study that needs to go into where that substation is going to get located. That's handled by our distribution planning in EEOA and the Electrical Engineering and Operations Administration. There's a department that they do all of our planning. Okay. And so there's distribution planners who are looking at the loads that are coming on. They're monitoring issues on the lines to see if we are having some voltage issues or where we would benefit from having more capacity or more strength added to our system. And they identify where the optimal location of a switchyard of a substation is going to be. It is really important to get the substation where the load needs to go.
Absolutely. That makes sense. All right. So in terms of size, what is TID's largest substation?
Physically, largest substation is going to be our Walnut 230 kV substation. There are other 230 kV substations that we're attached near to, but what is wholly owned by TID is going to be our Walnut 230 substation. And that is probably about 5 times larger than what an average distribution substation would be.
Okay.
And there we go from our 230 kV voltage down to 69, as well as 115 kV from that location.
Okay, great. So then, similar question, but the inverse. What is the district's smallest substation?
The smallest substation is our college substation, and it is really more of a tap substation. So it's also unique in that way, where it's located off of a transmission line. We basically connect into it. We have a transformer, we have load, and there's not a lot of protection that we could do from that facility. And the protection on that line ends up happening at 2 other substations, just based on how it's connected to our system.
So you would define you said a tap line as, how would you define that?
The tap would be something that doesn't have a way of really interrupting or protecting itself.
I see.
We do have some protection that happens at a tap from the transformer. There's fuses that feed that transformer, but we're not able to, essentially it's residing on a line that's protected on both sides with interrupting equipment. And so it's kind of at the whim of that line.
Okay.
And so it may have nothing to do with anything nearby, but if that line needs to go, the station's going to go as well.
Got it. Okay. Okay. Now, you said that that the substation that's located near WEC, the Walnut 230, is about 5 times the typical size of a distribution substation. Is there kind of an ideal size for a substation? Or, I mean, I know if you drive around town, you'll see all different sorts of configurations. Is there kind of, in your opinion, a perfect size?
Substations can really vary in size, and it does depend on the system where those substations and their standards. For TID specifically, we have more of a rigid bus design, or we kind of have a footprint that we're looking to achieve. And so with that, we want to have a substation that's going to allow, or we want to have a parcel of land that's going to allow access into the substation, maneuverability within the substation. If we need to bring in large equipment like our transformers, if we need to cross canals, which we do in some cases, we want to be able to provide as much maneuverability within that footprint as possible. I would say that if you're looking in the 3-acre standpoint, that's going to be the minimum footprint that you'd want to go with, and then hopefully up from there. I mean, really, we'll take what we could get in the substation.
Sure, absolutely. And we'll talk a little bit more about that, you know, when there's a need has been identified and a new substation has to go in, like you said, there's a little bit of kind of working with what you can get your hands on. But that does make a lot more sense. You know, I've driven by a few substations and it's large equipment to start with, but you don't think about when we have to get other large equipment in there to do maintenance, to do the work, that they need a little bit of room to navigate.
Right. And especially if we're pinned in on all sides, either by neighbors or other infrastructure.
Yeah, right. Okay. All right. So as we've discussed, substations obviously play a critical role within the district's electric system. And as such, TID is actively investing resources in upgrading many of our substations, especially over the next few years. One of our substations has already received a fairly substantial upgrade. Can you tell me about the Roding substation?
Yes, Roding is a substation that was built, I believe it was 1968 originally. It's located right off of the Syrian Main Canal and Roding Road. It had original footprint. There were 2 lines coming in, 2 transformers serving 2 banks of load. When we decided, or it was identified that we needed more capacity in the area, and that was because we were seeing these loads coming up in the Sirius. Sirius is a high growth area for us right now.
Sure.
And we were seeing that our capacity of our transformers were kind of exceeding the maximum of where we feel safe operating them. And so we needed to add capacity to the Roding substation. And to do that, the investment of a new transformer, that's a very hefty weight in terms of price. It is going to range somewhere between the $2.5 million to $3 million per transformer.
Wow.
So it's very important that with that we provide good protection to the transformer, think about it from a risk assessment standpoint, make sure that there's fire protection or consideration for if something were to happen to one transformer. We definitely wouldn't want that to happen to a second transformer.
Absolutely.
So we went about procuring the transformers. We also had to change the spacing in the substation to allow for the transformers. They were pretty close together.
Okay.
So we had to spread those out in order to fit them. And then we also wanted to add protection to the high side and the low side of those transformers. That protection allowed for us to put in a differential scheme for the transformers, which is the fastest and most sensitive type of protection that you could get.
Okay.
So with that, we needed to put in some new circuit switchers. And with that, we needed to make room where there wasn't any. So we did end up going vertical on a few of the assets in that roading switchyard.
Oh, interesting.
Yes. So ideally, you'd be able to spread out and have all the room that you wanted, but we're really limited. The lines need to come to the transformers in that location, and the transformers need to go to the distribution bus in that location. So you kind of want to maintain these orthogonal approaches if possible. And so with that, to fit in the space that we had, I ended up going vertical. So we have a new type of switch that we brought into play, and we have a vertical circuit switcher that we brought into play on a very small base in order to do the isolation that we needed. A circuit switcher is kind of like a circuit breaker. It doesn't have the same level. It's not required to meet the same criteria. So it's kind of like a circuit breaker junior.
Okay.
And that it is able to do protection for transformers. So they're very suitable for that. So we essentially rebuilt all of the 69 kV in order to allow for those new transformers to go into place. Okay. And then with that, we had basically rehabbed the entire 12 kV as well, because we were seeing some of our steel structure deteriorate.
Oh.
So it's essentially a brand new station as of 2025.
Okay, excellent. And then, as I understand, there was also kind of some additional uniqueness to this particular substation. You mentioned it's right next to the Ceres main canal. What issues did you run into with that piece of infrastructure? Yeah,
that's a really good point, actually. So one of the challenges, as I mentioned, is we were trying to get additional capacity out of this substation. But because of how it was originally built, there was a shared vault where we put our distribution feeders in.
Okay.
And by having that shared vault, it actually caused more heat to be generated from neighboring conductors. And so in order to operate safely and to make sure we didn't damage those conductors, we actually had to derate or reduce the amount of capacity that each of those lines could serve. Okay. So we were kind of in a situation where you could add more capacity for the transformer, but you couldn't get the capacity out on the distribution system.
Okay.
So line engineering, and we had discussed with them, as well as distribution planning, and determined to remove that shared vault and then individually route the distribution feeders out of the substation, which is very challenging to do because we had a few of our feeders that were already traveling underneath the Ceres main canal. So we coordinated with line engineering, coordinated with line department, coordinated with civil engineering, hydro, to figure out how to get those feeders out from the distribution bus and get them underneath the feeders and up on the pole to feed to our customers. So it was an extensive effort. We ended up doing the full scope of the work over 2 pretty big outages. The first one was the distribution outage, and that happened in the late or winter 23, spring 24, and then we completed the 69 kV, including energizing the transformers to the system in basically May of this year, 25.
Okay. Wow. My goodness. And so obviously it was a multi-year project. When did the planning for this upgrade actually begin? How many years in total went into this upgrade?
Yeah, so with roading, we actually have been working in one capacity or another probably since 2018. I'll be very happy to put that one on the shelf at the end of this year. But we did some work prior to identifying the capacity issues that we had there. So one way or another, we've been planning and replacing since 2018.
Okay, my goodness. And you mentioned the distribution planning, you mentioned line department. Is it TID folks who are actually doing the work when it's time to make these replacements, do this rebuilding of a substation?
Absolutely. If we can work with TID folks to do the work, then we know that we're going to get a good outcome. The line department, a big part of what they have contracts with are boring. They have boring contractors. And so we have good relationships with boring contractors. They do a lot of planning, work with the cities when we need to be boring outside of the switchyards proper. Took all the requirements that civil, that hydro needed, and were able to implement it. So that was on the line side. Within the switch or substation itself, well, I do the capital planning, identify what equipment that's needed, procure the equipment. That's a big part of my role. I work closely with engineering tech group, specifically Regina Trevino and I were working with this project for many years. And she is the one who is going to do the drawings and the construction effort that show what protection that we need, figure out where the wires need to be run to, what piece of equipment needs to, and where on each piece of equipment a cable will land. So she does all of the electrical side of that. That includes the schematics, wiring diagrams, cable schedules, things like that. But she also did a lot of the structural in this regard. So she had a structural background. So from that, she's very, very adept in the structural world. So she and I, working with the structural engineer, we did have to consult with a structural engineer on this one. And actually on every project that we're going to do, where there's going to be some structural involved. So we want to make sure that we were working with the right people in that regard. But we took the structural engineer's requirements and put them into drawings, detailed out the steel drawings. Those got handed over to the weld shop, who built every single piece of structure that's physically located in roading. I personally think that we did an excellent job. It went in well. We got a lot of kudos from the substation guys, who are the ones who had to set every single piece of steel. And then they also did the assembly of the bus, installing the circuit breakers, wiring the circuit breakers, connecting the circuit breakers up to the high voltage connections, testing the circuit breakers. We had electronics who were in testing the relays, making sure they did everything that they needed to do, implementing the protection scheme that was developed by Tracy Toops, who is our protection engineer. So, I mean, it's definitely a homegrown project, and we're very, very proud of the outcome.
Right on. Very cool. Yeah, it definitely sounds like all hands on deck. There were a lot of different TID, areas of TID that played a role. That's really cool.
There were. And I did want to mention, like, line department, when they came in and they made connections to our 69 kV lines that they brought in and connected to the structure. I mean, honestly, those guys are so good at what they do. And they do it up in buckets, 30 feet up in the air. And it was just extremely impressive to watch everything come together.
Oh, excellent. That's really cool. Okay, so there's another substation that is on the list for an upgrade in the near future, the Fairgrounds substation. What's going on out there?
With Fairground, we're seeing some of similar, themes running through our substation improvements, especially as we put in these really expensive pieces of equipment like a transformer. We want to make sure that we have that fast protection. We want to make sure that we keep as much of our system in service as possible. So we want protection that's going to be specific to the transformers, that are going to maintain continuity to everything else that's coming from there. So we're building a containment, and that's for environmental protection. There's a lot of oil in these transformers. We want to make sure that oil doesn't get into the soil. Sure. But we're also using those containments as part of our fire protection and maintaining that space and making sure that if there was an event where oil came out of the transformer, that transformer fire wouldn't spread to a neighboring unit. So same kind of thing, containment, protection. We're also looking at redoing the 12 kV structure that's out there. The one that we have is just, it's very hard to work within. It's got a very small footprint. The equipment is really big. That puts our guys kind of into more, or we want to have the safety and to keep them out of precarious situations. We want to give them the space that they need to get in and around their equipment.
Makes sense.
And then with that, we also don't have a maintenance breaker at Fairground, and it gets harder and harder to take outages on pieces of equipment. So if possible, we want to have that way of continuing to serve that load while working on the equipment.
Okay.
So we're going to give maintenance and a maintenance breaker with the transfer bus, essentially, to allow for that continued load serving capability.
Okay. So there wouldn't be a break in reliability then. We would be able to do the work we need to do without taking that particular neighborhood or community out of power.
Right. We would like to keep every single line in service if we possibly can.
Absolutely. Okay. All right. So in addition to some of these substation upgrades, we also have plans to build a couple new substations from the ground up. Can you tell me about those two substations and kind of where we're at in that process?
Right. So these stations have been identified from our distribution planning group as we want to make sure we're able to serve new load that's coming into our system. We're in one of the stations is planned in a more rural western side edge of Ceres.
Okay.
So in an industrial arena in Ceres where we're seeing a lot of that growth and we don't have a lot of capacity out there right now. This station is going to be located, and when it's located, it's going to help offload other stations to allow more load to be served by those stations. Our plan for that, we are very focused on reliability. And so with that, we've chosen to go with a more reliable configuration. And for that, it's going to be a ring bus.
A ring bus? What does that mean?
So a ring bus means that the load or the lines will come in and essentially create a loop within the station itself. And so it allows for lines or load serving capability to come from one side of the station or another. And then with that, it also has protection on our transformers. The main reason that we have the ring bus is for reliability, like I mentioned. So what happens is instead of having one breaker that the line feeds into, the line will actually feed in between two breakers. And these breakers are set up like a ring, which is why it's called a ring bus.
Okay.
So that allows us to work on one breaker or the other, and then the line is able to go, if usually it comes in and it's split between the two breakers or whichever way it's going to naturally flow, it allows for that line to come in and still be able to service the load in that area or even to loop through the other line, but you could still take a breaker out of service.
Okay.
So when you take that breaker out of service, you're not losing any reliability in terms of the amount of lines that are in service.
Okay.
So it allows for breaker service or for maintenance and upkeep, where otherwise you'd have to take that entire line out. And as you take lines out of service, then you are reducing the reliability of the system as a whole.
Okay. And the ring bus that you were talking about, is that a pretty common design within TID's service area, or is that something that's a more new and modern design?
No, we do have a few ring buses on the distribution side of things. We have one for sure, Commons, Marshall. We have one in August. So this isn't new to us.
Okay.
What we are doing is instead of kind of realizing later, we should put a ring bus in, we're starting with the ring bus as our lowest level of reliability. And there's more investment involved with that, but also we have less risk that we will be impacting either our transmission system or our distribution system by putting in this more reliable configuration.
Okay, great. And so we have a plan to purchase the land to build this new substation, but I understand there's kind of a unique configuration to the area.
related to the new substation in Ceres, we are looking at a parcel of land where we actually have a house located on the corner. So it creates a little bit of a L shape around this house. So, and so we know what the footprint is going to be. And this is something that is happening, at the AGM level, trying to identify the parcel and negotiate the price and board approval. And so that process is going on right now. But at this moment, it looks like we're going to have an L-shaped parcel.
Interesting.
And so determining how to best get the transmission lines in and the distribution lines out, those are really going to depend on what land we have to and what we have to work with within that space.
Yeah, absolutely. And I think that's a really interesting part of it is, as we've mentioned, the substations get placed based on need, based on where we need capacity to serve load, based on where there's new growth, et cetera, et cetera. And sometimes these are neighborhoods that are built out to a large extent. And so we kind of have to work with what's available to us. And I think that's where some of your talents in creating these different designs, like we talked about earlier, whether you spread it out or you build it up or whatever the particular parcel warrants.
Right. And a lot of that has to do with working with the load line engineering side to determine what is constructible on the line side as well. So we do have to collaborate closely in there to be able to identify the final layout within a substation.
Very interesting. Okay, great. And then in addition to the new substation that's being built in Ceres, there's also one being developed for Patterson. Is that right?
Yes. So Patterson is seeing a lot of growth on the large industrial side. We're seeing a lot of warehouses going in. So there's a lot of load that is being served or needing to be served there. We're also seeing charging stations because it's on the I-5 corridor.
Sure.
So we have identified a new customer that wants to come in and requires a pretty large load serving capability. We're already having some challenges there with being able to provide back feeds, which means that if you're going to take a certain section out for maintenance or otherwise, you want your neighboring station to be able to feed those and to have that, again, that reliable service. We are excellent at providing continuity of power to our customers. So we want to maintain that capability, and to have growth, you need to have backfeed capability as well.
Yeah.
So we have the load and we need the backfeed capability. And so we are looking to add that third station in the Patterson area.
Okay, great. All right. So you've mentioned load growth. You've mentioned capacity in different areas. What are some of the other reasons why we might either build a new substation or upgrade existing substation equipment?
A lot of it has to do, and what we're seeing out there is just older equipment. There is a lifespan. There's a life expectancy of the equipment. We have great and invested substation crews who are paying a lot of attention to it, doing regular maintenance and maintaining visual monitoring and trending of the equipment that we do have. But at some point, it's got to be replaced. And so we are seeing, depending on who you ask, they may have a life expectancy over a circuit breaker from 25 years, 40 years. In some cases, we're sitting at 55 plus years on some of our equipment. So it is time to get in there and to do these replacements. Similar to what I mentioned before about the transformers, we have some very old transformers. Some are approaching 65, 70 years old, and they've been in service for that entire time. So, planning for their replacement, but how do you do that? What's the cost? What is the investment that we want to make in terms of making sure that we protect the transformer, we have that good protection, but we also keep our customers in service. So there is a lot of balancing and looking at the budget, looking at the risk to determine what any scope would be, especially with replacing transformers. But specifically where we have transformers near neighbors, we're going to make sure we have the proper investment to keep those neighbors safe, to keep the outages short, to keep our assets viable.
Right. Absolutely.
To the extent possible.
Yeah. Now, do you ever run into a situation where, let's say you have an older substation and the transformer needs to be replaced? In bringing in a new transformer that is now, 40, 50 years younger potentially than the existing transformer, does that then affect what you're connecting the equipment you're connecting that transformer to? Like, is there a development in the sophistication of the equipment that would then kind of beget replacing more equipment?
It happens mostly from a spacing configuration, being able to fit these new elements, like I mentioned, circuit switchers or circuit breakers, that where there may not have been circuit switchers or circuit breakers before.
Okay.
So if you look at a $6 million investment in transformers, do you need to also look at a $500,000 investment to make sure that they are positioned such that they're protected from fires, have the best protection, these types of things. And it's just, these are conversations that we're having on a regular basis to determine to what extent these improvements and what they need to look like. But from my standpoint, we are going to want to put this infrastructure into place and have it last for another 50 years or 60 years or however long that the old one was there for. And so to do that, we want to make sure that we have the protection in place. We can have a serviceable station. The substation crews can get in, get around, and get to where they need to get safely and limit the amount of outages that our customers will have to experience.
Okay, excellent. So we talked about the specific timeline when you were doing the upgrades at Roding Substation, but in general, what goes into building a new substation and how long does a process like that take?
It's going to depend on the system or the essentially the established processes any system uses to bring in a substation. We are not investor-owned utilities. We govern ourselves, right?
Okay.
So that's very helpful. It cuts down a lot of timelines associated. But we do want to follow kind of a standard approach to every substation.
Sure.
So once the substations are identified where they need to go, they obviously need to get into our capital budget and the planning for the substation in terms of budget. Then there's the procurement of the land, and that's an effort, and that's proving to get more and more challenging.
Sure.
Especially in California.
Absolutely.
So we are working on procuring, and then from that, there's going to be an environmental process. We're part of California. We go through the California Environmental Quality Act and the processes that are associated with that. So depending on what voltage class, the amount of capacity will determine what level of report that's required. Generally, that is going to be a 12 to 18 month process, and it's going to involve public review and approval, and then ultimately getting to the board to get the go-ahead from the board after the report comes out and any mitigations have been accepted and determined as a response to an environmental impact report or whatnot, whatever level of CEQA that's required.
Yep.
So CEQA review, and then from that point, when we have the footprint established, then we can determine what that layout's going to be. From the electrical side, this isn't something that is really as obvious, but we're able to do quite a bit of electrical design without knowing what the specific spacing between equipment is. That all happens with that instrumentation that I mentioned, like the current transformers and the voltage transformers and the relays. And we know we're going to have a building. So we have to go through the layout, any permitting that's associated with it, if we need to do septic, if we're tying to the city sewer, any of those kinds of things will need to be determined, studied, and implemented. But from a procurement standpoint, where we're really struggling on is lead times in the industry. And our transformers, they range 3 to 4 to 5 years, just depending.
Oh, wow.
We are definitely having to be very creative in planning for transformer replacements, especially looking at a 5-year capital plan. You can only know so much of what's coming 5 years ahead of time.
Sure.
And so we're doing things like procuring manufacturing slots for these transformers to be able to pull the trigger necessarily when it comes time to determine what design is needed.
Right.
Same thing with circuit breakers, especially at the higher voltage level, at the 115 kV level and above. We're now in a new environment from a regulatory standpoint related to SF6 gases. We use a very specialized insulating gas in our circuit breaker, and in California, they're trying to phase this out.
Oh, okay.
But a lot of the equipment is very new, very novel, and how to implement this equipment or go about that. And still, even without that level of complexity, there's 2 years lead time minimum to get circuit breakers. So
wow.
At this point in time, it is going to take you somewhere in that 4 to 5 year to, in the best case, to get a substation planned and built.
And that's just to get all the right pieces together in the right spot. Then you go into the actual building process.
Yeah, absolutely. You are finding that if you want to try to get a substation up and running, you're not necessarily going to have all your equipment there waiting. You're going to have to start that construction ahead of time, waiting for that equipment to arrive and landing where it needs to land. So yeah, it's definitely a challenging time in the substation arena.
Absolutely. That's what it sounds like. So given TID's commitment to reliability, and as you mentioned, these, the long lead times that go into whether it's remodeling or building new substations, how is TID preparing internally for the existing and the projected substation needs for the next 10, 20 years and beyond?
You're right. It is pretty challenging right now. And there's a lot that goes into a substation. So for having the aggressive trajectory that we're looking at with the number of substations and the improvements that are needed on these substations that we're starting to address now on like some of our substations built in 1955 and the improvements that are required there. There's a lot of time that goes into that, and we don't have a lot of people. We have been fortunate to hire a second substation engineer.
Oh, great.
As far as I know, it's the only time in TID's history that there's been more than one substation engineer.
Wow.
And she is doing a lot looking at these additional requirements in light of the regulatory with the CARB and the bringing on the new equipment and how we're managing that. But she's also looking at the capital improvements that are needed with our aging infrastructure, with our old switches and our old transformers. So there's going to be a lot of study to make sure that we are spending in a way that makes sense to keep as much reliability to our customers as possible. So we're very happy to have her. The other thing that we're doing is we're having turnover. We're having people retire. We're having a succession planning in our engineering technician core. And so with that, we have 2 brand new substation engineering techs working for us. But in the meantime, we've been fortunate to be working with consultants that we're, growing relationships with and who are learning our ways. So we're going to be leaning on them quite a bit in the coming years from an engineering side as well as a contractor side.
Okay,
so
very good.
It's going to be new, but it's what we need in order to keep up with the demand of our customers for the need to address our infrastructure.
Absolutely. And again, maintain that reliability.
Absolutely.
Excellent. All right, Janis, well, before we let you go, any parting thoughts that you wanted to leave us with regarding substations?
Only that I look forward to every day and all the challenges that are going to cross my plate. I am never bored, and I have the best job in the world. So
fantastic. Well, and we are all very thankful that you have the job that you do, because you do great things for TID. So thank you for that.
Thank you.
Thank you for tuning in to the TID Water and Power Podcast. You can find TID on Facebook at facebook.com/TurlockID, on Instagram and Twitter at TurlockID, and on LinkedIn as the Turlock Irrigation District. I'm your host, Constance Anderson. We'll see you again next time.